Okay, so it's a great pleasure to introduce Christoph Aistleitner from Graz University. And he's going to talk today for us about a guide to uniform distribution model 1 and discrepancy. So Christoph, you can start at any time.
Yes, so thank you very much for the invitation. It's my great pleasure to be speaking here. Bad luck that I couldn't come physically to Brazil and have to give this talk online. I've been to Brazil just once in my life for the ICM in Rio, and I have very good memories of that. For the following week, we went to a conference in Salvador de Bahia, which was also very nice. One of the things I remember most vividly is that it was incredibly noisy. So they were playing their drums there in the city center every day until maybe 2 in the morning before finally they stopped making the noise. That was very impressive. So in Europe, everybody would be jailed within minutes if you try to make this kind of noise in the night. No, I have very good memories of my trip to Brazil. Okay, so the talk here is a kind of survey style talk on equidistribution and discrepancy. That's a topic where we have a long history in Austria, and many people work on this kind of topic in Austria. This will stay on a rather basic level, so my apologies to all those who have seen this kind of mathematics before. So probably for you, there will not be so much new material. So the starting point here is Dirichlet's approximation theorem, which is something that certainly most of you have seen. So this says that if you start with some irrational number alpha, then you can find infinitely many coprime solutions P over Q to this inequality here. And now the perspective that we will be taking here is we can multiply the whole equation by the denominator of this fraction here. So we can multiply Q up here such that we get Q alpha. And now I'm not writing Q anymore, but I'm writing N instead of Q because it's not a denominator anymore of a fraction. And then what this statement says here is that Q times alpha or N times alpha minus some appropriate integer, this difference can be made small, or in other words, N times alpha can be made close to an integer. So the fractional part of N times alpha or N times alpha mod 1, I can bring this very close to 0. And then it's a natural question to ask if there's something special about the value 0 here, or if this could be anything else as well. And as it turns out, there's nothing special about 0. That's the message of the Kronecker approximation theorem, which says that when we look at all these fractional parts, N alpha mod 1, so alpha is a fixed irrational, N runs through all the positive integers, and then this sequence doesn't only have an accumulation point at 0, but this sequence actually stands in the whole unit interval. And this is still not the end of the story. There is an even stronger result. For that, I have to introduce the notion of uniform distribution modulo 1 or equidistribution, and you can see it here on this slide. So we have a sequence of elements of the unit interval, such as these fractional parts of N times alpha. And the sequence is called uniformly distributed modulo 1 if this asymptotic relation here holds. So what happens here? So this is an indicator function of an interval. We're counting how many points of the sequence we find inside of this interval. So we count with index up to capital N, how many elements of the sequence are contained in this interval. We divide by the total number of points. So that's the overall expression here is the relative number of points that are contained in this interval. And if this relative number of elements of the sequence, if this converges to the length of the interval, and if this is true for all intervals that are contained in the unit interval, then we say the sequence is uniformly distributed. So uniform distribution, it's something stronger than being dense. It doesn't only mean that all points are accumulation points. In all small intervals, we can find sooner or later 1 point, but it says asymptotically, whenever we fix some interval, asymptotically, the number of points we find inside of the interval is in proportion with the length of the interval. And a classical perspective to take on this is that uniform distribution is a kind of pseudorandomness property, because when you start with an IID random sequence, which is sampled with uniform distribution in 0, 1, then almost surely you will get this behavior. So that's in probability, this would be called the Krivenko-Cantelli theorem, that the empirical distribution functions on the probabilist would see here on the left-hand side some empirical distribution function, and on the right-hand side he would see the underlying distribution, and here the one would converge to the other as it does in a random situation. One of the foundational results of the whole theory is now the fact that as an improvement of Kronecker's approximation theorem, the sequence n alpha mod 1 is not only dense in the unit interval, it's actually uniformly distributed mod 1 in the unit interval. So it means each subinterval of the unit interval contains asymptotically its fair share of points. Of course, it's crucial for the result that alpha is irrational. So if you start with some rational number alpha, you can never expect to get uniform distribution in the end, because the set of points that you see, they're all rational points with a fixed denominator. So it's necessary that alpha is irrational. But once you get rid of this trivial obstacle that rational alpha is not allowed and assume that alpha is irrational, then you get a result which says, okay, always you get uniform distribution mod 1 of your sequence. And there's a whole slew of sequences that are known to be uniformly distributed. So some are written here. So that's polynomials times alpha mod 1, powers of n mod 1, powers of logarithm mod 1. In all cases, you have to exclude the trivial obstacles. So in the case of this polynomial sequence times alpha, alpha is not allowed to be rational. In the case of powers of n, of course, alpha is not allowed to be a positive integer itself. But once you rule out the trivial obstacles, you get many, many examples of sequences which are equidistributed. And all of this is classical work. So this was done in the 1920s, 1930s by Weyl, van der Korput, Koksma, I don't know, several other people. So this is a very classical theory. And I think it's fair to say that this whole theory of equidistributed sequences in the unit interval is quite well understood now. So here again is the definition of what it means that a sequence is uniformly distributed. Relative number of points in an interval converges to the length of the interval for all intervals that are contained in the unit interval. And now to quote Hardy and Littlewood, who have also been working on this, and simple but ingenious observation of Hermann Weyl is that you can read this definition in a kind of functional way. So you can read this as saying an average of function evaluations converges to the integral of the function. So that's exactly what we have here in the definition on top as well. This is an average of function evaluations. The functions are indicator functions of intervals. And on the right-hand side, we see the integral of this indicator, which in the case of the indicator is just the length of the interval. And as Hermann Weyl realized, you get an equivalent definition of uniform distribution if you change the class of test functions. So instead of all indicators of intervals, for example, you could say you demand this relation for all continuous test functions, for example, and you get the same notion of uniform distribution. So these are equivalent characterizations. Or one other way to do it is to take as the class of test functions, the class of all complex exponentials. And because they, by the Weierstrass approximation theorem, because they are dense in the class of all continuous functions, you again catch the correct definition of uniform distribution mod 1. And this gives rise to the famous Weyl criterion, which says that a sequence is uniformly distributed mod 1 if and only if this average of evaluations of complex exponentials, if this converges to 0 for all non-zero frequencies h. So really, this is also something of the form sum of function evaluations at the points of the sequence converging to the integral of the function. The functions here are these complex exponentials. The integral is just 0. And this gives an easy tool to determine if a sequence is uniformly distributed or not. So all the examples I've shown before, such as polynomial times alpha, all these examples were established using this criterion here. And as we all know, in number theory, there are many tools for bounding the size of exponential sums. And this criterion here establishes a relation between the concept of uniform distribution mode 1 and the problem of bounding the size of exponential sums. So that's how this comes together. So here's a picture of Hermann Weyl together with his mentor, David Hilbert. So this famous paper of Hermann Weyl where he established the Weyl criterion, this was published in 1916 in Mathematische Annalen. And this remained the only paper of Hermann Weyl that he ever wrote on uniform distribution. So he really laid the foundational stone for the whole theory of uniform distribution mode 1 in this paper. Many ideas that became very influential later are already in some form contained in this paper. And then I think in maybe 1916 or 1915, he got a position as a professor at ETH Zurich and went to Zurich. And this was the time when Einstein also was working in Zurich and was developing his theory of relativity. And quickly, Hermann Weyl became enthusiastic about these physical aspects or these mathematical physics questions. And he left uniform distribution theory forever. So he wrote one single paper on the topic, but one that became very, very influential. And later never returned to the topic again. So here is a famous application of the Weyl criterion. So as I said, n times alpha for alpha irrational is uniformly distributed mode 1. There were proofs of this fact without Weyl criterion, so it's possible to do it. It's very cumbersome because if you really understand this in terms of counting points in intervals, you have to do a lot of combinatorial work and Diophantine approximation work. If you prove this using the Weyl criterion, it's very straightforward. It's very simple to do it. So the proof is just this single line, this one equation. Given some frequency h non-zero, what we have to do by the Weyl criterion is show that this sum here, this exponential sum, goes to 0 as n goes to infinity. Now, the sum on the left-hand side here, this is just some geometric sum. We all learned in the first semester of our calculus class how to evaluate a finite geometric sum. So there's an explicit formula for this. Now on the right-hand side, we get some expression. It's crucial now that alpha is irrational. So because alpha is irrational, this quantity h times alpha can never be an integer. So this complex exponential here in the denominator is some constant, but the constant is not 1. So the whole denominator is non-zero. So that's some fixed quantity, which is not 0. Here there's something that's between, between 0 and 2 in absolute value. So the whole thing on the right-hand side here is this bounded quantity times 1 over n. This remains bounded, 1 over n goes to 0. So the whole expression goes to 0, whatever h is. And we proved that n alpha is uniformly distributed whenever alpha is irrational. So using the Weyl criterion, this is a very, very simple statement to prove. So I said already that equidistribution traditionally is related to pseudorandomness. And there's another concept about pseudorandomness that's closely related with equidistribution. That's the concept of normal numbers. So a real number alpha is called normal number in some base b if the sequence b to the n times alpha is uniformly distributed mode 1. So that's not the classical definition. That's an equivalent definition using the language of uniform distribution. The classical definition of normality would be, so you have this real number, you throw away the integer part, you only care about the part after the decimal point, and then you start counting how often you see a certain digit appearing in this decimal or in this base B representation, and if all digits appear with the same asymptotic frequency, and if all blocks of digits appear with the appropriate asymptotic frequency, then you call the number normal. And the famous result of Emile Borel asserts that almost all numbers in the sense of Lebesgue measure are normal numbers. And in principle, of course, you could establish normality using the Weyl criterion, but as it turns out, it's actually very, very difficult to find the number that is normal. And given some naturally occurring constants, such as square root 2 or e or pi, it's actually more or less impossible to say anything about the normality of such a constant. And now from this point, we could take a road. So there, we could now go into the direction of pseudorandomness of sequences of digits. And that would be a very interesting direction to take. In his book on the art of computer programming, Donald Knuth spends a lot of time speaking about pseudorandomness properties of finite sequences of digits. There is the very influential and interesting work of Modulo and Sarkozy, where they introduced different measures of pseudorandomness for sequences, for finite sequences of digits. One of them being based on the equidistribution property of b to the n alpha that we saw on the previous slide. That would be a very interesting direction to take, but we're not going to go in this direction. Here is the only Brazilian connection of the whole talk that I'm giving here. So there are two beautiful papers on, one is on the minimal possible values, and one is on the typical values of these measures of pseudorandomness that Modulo and Sarkozy introduced. Both are very interesting questions. So given some measure of pseudorandomness, what should the typical size of this measure of pseudorandomness be? How small can you make this measure of pseudorandomness? And one of the co-authors of this paper is Gugu Moreira, whom probably everybody here in the audience knows. And I should also mention that in these papers, there's many results, but there's also many open problems, and several open problems are still unsolved. So there's still quite a bit of work to do in this context. So if you find that interesting, here's the reference for these papers, and you can do some work in this direction. Now, this is a possible direction, but we're not going. Yeah.
Just a comment. I think the second name, which is Japanese, it's also a Brazilian person.
Ah, I didn't know that. I was not aware of this. Okay. So that's a double Brazilian connection. Okay, thank you.
Christian Modulo was almost Brazilian.
Yes, he counts as half Brazilian, maybe. Yeah. That's right. Yes, I lived in Japan for some time, and I know that in Brazil you have a big Japanese community. There was a period in Japanese history when many people left Japan and to find jobs in Brazil. So this doesn't come as a total surprise. Okay, I wasn't aware of this. Okay. So this would be one possible direction to go, but we're not going in this direction. We're going somewhere else. So instead of speaking about pseudorandomness of sequences of digits, let me introduce the concept of discrepancy. So the equidistribution, the definition of equidistribution that we've seen before, this is a qualitative definition. So a sequence is equidistributed or it is not equidistributed, but there's nothing in between. So either it has this property or it does not have this property. And the concept of discrepancy tries to quantify the degree of equidistribution of a sequence. Okay, so here you can see the definition. So you get some points in the unit interval. Then again, you take this average, so you calculate the relative number of points inside of an interval, you compare to the length of the interval, and now you take an absolute value of this difference, and you take a supremum over all available intervals that are contained in the unit interval. So this is called discrepancy, and it's very easy to see that a sequence is equidistributed if and only if the discrepancy of the sequence tends to 0 as n increases. So equidistribution is a qualitative property, and discrepancy allows you to do more. So for example, once you know that a sequence is equidistributed, you can ask, okay, I know now that the discrepancy tends to 0, but how quickly does it tend to 0? And we will see later why this is an interesting question.
Christoph, I have a question here. So is really if and only if, because it seems that the discrepancy goes to 0 is more stronger than equidistribution, or no?
Yes, it looks stronger, but it's really an if and only if.
Okay, thanks.
So yes, so in principle, like if you have to prove this equivalence, then one direction is trivial and the other direction is more complicated. You have to do some work, but it turns out that the two notions are actually equivalent.
Okay, thank you.
Okay, so so this allows us to somehow quantify the quality of the equidistribution of a sequence. So for some sequences, this convergence will be faster, and for some it will be slower. And we will see why this will be important. The discrepancy of a finite point set, to minimize this is a trivial problem. So if you need to take n points which have a small discrepancy, you just put n points on an equidistant grid in the unit interval, and it turns out the discrepancy is 1 over n, and this is minimal. But it becomes an interesting question once you have to do it with an infinite sequence. So it's known by a result of Schmidt that for an infinite sequence, you cannot have such a small discrepancy for all n, but infinitely often your discrepancy has to be as large as log n over n. So if you want to construct an infinite sequence, then you get this extra logarithmic factor here. And it's also known that this can be achieved. So for some sequences, this is also an upper bound. So in this one-dimensional setup, the problem of minimizing the discrepancy is understood. So coming back to the sequence that we've seen at the beginning, the sequence of fractional parts of n alpha, the discrepancy of this can be, as it turns out, the discrepancy of this sequence is very closely connected to the sequence of partial quotients in the continued fraction expansion of alpha. So if alpha is some irrational number, then we take all these fractional parts of multiples of alpha, fractional part alpha, 2 alpha, and so on up to n alpha. I'm sorry, that should be a capital N here. That's the last point in the first n elements of the sequence. So then the discrepancy of this can be bounded in terms of the sum of the partial quotients in the continued fraction expansion of alpha. And so as you see here, the summation has to go up to the partial quotient, which is associated with the continued fractions denominator, which is roughly of size n. And this implies, if you calculate a bit, that if alpha is badly approximable, which means that alpha has bounded continued fraction partial quotients, then the discrepancy of n alpha is of order log n over n. And as we've seen on the previous slide, this is the minimal possible order. So this is one example of a sequence achieving the smallest possible order of discrepancy of any sequence in the unit interval. This sequence n times alpha mod 1 for some badly approximable alpha. Okay, so now we know what discrepancy is. There is a device that allows to establish to estimate the size of the discrepancy of a sequence. So I don't want to go into too much detail here. The point is just, if you want to calculate or estimate the size of the discrepancy of a point set, there is an inequality called the os-Turan inequality, which allows you to estimate this in terms of certain exponential sums. So we've seen in the Weyl criterion, the qualitative theory of equidistribution can be characterized in terms of exponential sums. The Weyl criterion says something is uniformly distributed if and only if these exponential sums go to 0. For the quantitative concept of discrepancy, there's also something of this type. Discrepancy is related to certain exponential sums. So I don't want to explain what the formula exactly says. If you want to read about this, there's a beautiful exposition in the first chapter in Montgomery's book on 10 lectures on the interface of analytic number theory and harmonic analysis, where this is explained and developed in full detail. The point here just is, there is something allowing to estimate the size of the discrepancy of a point set in terms of exponential sums. And finally, so now we know that there exists a concept of discrepancy. We have seen that there is a way to estimate how large the discrepancy is. Now, finally, we also find an application for discrepancy. So now we also see that it's good for something. And this inequality is called Koksma's inequality. So we have a collection of endpoints in the unit interval. Then we have some function, which needs to be of bounded variation. And then we can compare this average value of function evaluations. We can compare this to the integral of the function. And the difference between the two is bounded by a product variation of the function times discrepancy of the sequence. So that's something that shows up very often in, say, analytic number theory, and probably also in many other fields. You have to estimate some sum of function evaluations. And then what this says here is, if the set of sampling points is, well, somewhat regularly distributed in the unit interval, then this average of function evaluations will be close to the integral of the function. So that's, of course, that's something that also an ergodic theorist would recognize. So for the ergodic theorist here, this would be points generated by some iteration of some dynamical system operating. But these points don't have to come from some dynamical system. This can be just any points in the unit interval. So once you have some information on the distribution of these points in the unit interval, you can run this machinery, you can compare this average to the integral. And the beautiful thing on the right-hand side is that here on the right-hand side in this error estimate, the influence of the function and the influence of the point set are totally separated, right? So here on the right-hand side, there is the total variation of the function, which is something that depends only on the function. And here's the discrepancy of the point set, which clearly is something which only depends on the point set. So the two influences on the size of the error, they are totally separated in this upper bound. Okay, so one way of seeing this is, you have to estimate such an average of function evaluations. You can compare it to the integral and you make some error. A second way of seeing this is, assume you want to calculate an integral of a function and you don't know how large the integral is. So it's a complicated function. You cannot say how large the integral is. One way of approximating the actual size of the integral is to find a set of points having small discrepancy, and then you calculate this average of function evaluations. And if your point set has a small discrepancy, then you have obtained a good approximation for the actual value of the integral. Okay, so there's these two different perspectives. Maybe you have to start with a certain point set and you have to calculate this sum of function evaluations. Then you can compare it to the integral. Or maybe you have to start with this integration problem. And then one way to approximate the integral is to use this average of function evaluations at at 0.7 small discrepancy. So that's, maybe that doesn't sound like something that you would be interested in doing, but actually, as it turns out, in higher dimensional problems, this is something that people really do. So in higher dimensional problems, there's a similar situation. Maybe you have a very complicated function here on the right-hand side. You have an integral that you cannot calculate. Now you approximate the integral, the actual integral, by such an average of function evaluations at smartly chosen points. That's called quasi-Monte Carlo integration. Okay, so that's one possible generalization of the whole theory. So you leave the one-dimensional case and you go to a higher dimensional setup. The points live in the d-dimensional unit cube. Instead of taking indicators of intervals, now you take indicators of axis parallel boxes. You define a discrepancy, which is the supreme over all such axis parallel boxes, comparing the relative number of points to the volume of the box. And then again, there's something like Koksma's inequality, and there again is something like the os-Turan. And really, this is something that apparently is used in practice by people in quantitative finance or in insurance mathematics. They have some integral that they want to calculate. They approximate the integral by an average of function evaluations at points having small discrepancy. And as it turns out, in higher dimensions, there also do exist points having small discrepancy. So for all dimensions, for all cardinalities, there exist point sets having discrepancy, some logarithmic factor divided by n. So it's a bit worse than in the one-dimensional case. In one-dimensional case, well, d-1 is 0, so this goes away. If you have higher dimensions, then you pick up some extra errors here. And as Klaus Roth showed in his famous paper of 1945 on the irregularities of distributions, you really need some extra factors. So given some dimension d, how small can the discrepancy of a point set of n points in dimension d be? Cannot be arbitrarily small. There is a factor which grows as the dimension increases. That's a truly ingenious proof of Klaus Roth, who won a Fields Medal in maybe 1956 or 1958 or something like this for his work on Diophantine approximation and what is now called the Roth theorem. But apparently Roth used to say that this was his favorite, the favorite proof he ever gave in his career, obtaining this lower bound here for the discrepancy in higher dimensional, in the higher dimensional setup. Now this was 70 years ago. Not so long ago, there was a small improvement of the result of Roth. So Billig, Lacey, Vagashakian, they improved Roth's result by adding here in the exponent of this logarithmic term a small quantity depending on the dimension. So now there is a plus epsilon d for some unspecified but positive epsilon d. That's the whole progress that we've made in this problem in the last 70 years. So this is considered the major open problem in discrepancy theory, to figure out what the smallest possible discrepancy of a point set in d dimensions is. The upper bound has a logarithm to the power d-1. The lower bound has a logarithm to some smaller power. The problem is to close this gap, and it seems that we are still quite far away from finding an answer to this problem. So here is a picture that I've taken from a talk that I had to give for a general audience in Austria for some pupils and teachers and the likes. So I was claiming, or I was pretending that I had to calculate an integral, and the integral is the, this is a part of the surface of the sea, and I want to calculate how deep the sea is on average. So here you have this dark shade, the sea is very deep here, the sea is very deep here, and there's these light shades, and the sea is not so deep here. And I want to calculate the average depth of the sea, and I cannot calculate this precisely. So I have my ship coming here, and the ship takes 100 measurements. So on 100 points, I can measure how deep the sea is, and then the actual average depth of the sea, which in mathematical language, of course, is an integral, is approximated by the average of these 100 measurements. And then I was telling this audience that, well, how do you choose your test points? Where do you make your measurements? Now, if you take random test points, maybe it works out well, but there's a chance, like in this picture here, that you're missing some very deep parts, or maybe you're missing some very shallow parts, and the errors will in general be large. And then instead, if you use a smartly designed deterministic sampling point set, then you can make the errors smaller. And then the question is, well, what is a smartly designed set of test points? So this one is not a smartly designed set of test points. This is an integration lattice of 100 points that's generated by this particular rational number. So in the end, I want to have 100 points. If I generate my integration lattice by this number here, 34 over 100, so it means the points are of this form, something over 100, something times 34 mod 100 over 100. So in simple language, that means you start here at the bottom, then you go 1 over 100 to the right and 34 over 100 to the above. Then for the next point, you go 1 over 100 to the right, 34 over 100 to the above. Then you repeat this, 1 over 100 to the right, 34 over 100 to the above. You leave on the top, you come back in here. Now, as we all see, this is not a very smart set of sampling points generated by this particular rational number. And now here's a picture for a similar integration grid, which is generated by a different rational number with denominator 100. And we see this looks much more regular. And the reason is, maybe not very surprising, something to do with continued fractions. So 34 over 100, it has one very large partial quotient sitting here in the continued fraction expansion. So, well, this one you can almost forget about. So that would mean the number we have here is almost 1 over 2 plus 1 over 1. So it's almost 1/3. Well, that's not very surprising. 34 over 100 is almost 1/3. So it's very close to a rational with small denominator. This does not give a very good integration lattice because this is very close to 1 over 3. We essentially get these 3 lines here. 1 line, 2 lines. Here is the 3rd line. The 3rd line is broken here on top and continues down here. So that's not a very good number to generate our integration lattice. And 39 over 100, well, turns out to be a very good number because all the partial quotients in the continued fraction expansion are very small. And now from here, again, there's many possible, very interesting directions that we could take. So the method that I sketched here is called the method of good lattice points. This is something that Zaremba was interested in and which led him to formulate the famous Zaremba conjecture on the existence of reduced fractions, which have, and I could speak about general constructions of low discrepancy point sets, and I could speak about harmonic analysis connections, and I could speak about numerical analysis connections. And we're not doing any of this. So if you want to learn a bit on the basics of uniform distribution and discrepancy, the standard reference is the book of Kuipers and Niederreiter. It's already 50 years old, but it's very easy, very pleasant reading, and contains all the basics of the whole theory of uniform distribution, mod 1, and discrepancy. So this is recommended reading if you find this topic interesting. Now, okay, now we're not going in any of these directions, but instead I will advertise my own most recent research. So we, together with Bence, Borda, and Manuel, Hauke, who are working with me in Graz in our department, we've just uploaded our brand new paper on arXiv a couple of days ago. The paper is called On the Distribution of Partial Quotients of Reduced Fractions with Fixed Denominator. And the point here is now to give one example of how this machinery of equidistribution and discrepancy can be applied in a real world mathematical research situation. So we tried to prove something about continued fractions. And as it turns out, we could use exactly the machinery that I've been trying to explain here. Okay, so what is this about? We want to say something about the continued fraction coefficients. These are called partial quotients. So these are the coefficients in the continued fraction expansion. We want to say something about them when the denominator n is fixed and A runs through all possibilities for getting a reduced fraction. And it was known for maybe 40 years what the expected value of this, well, this is this S of A over n, this denotes the sum of the partial quotients. Okay, so we have some reduced fraction A over n. We sum up all the partial quotients of this reduced fraction. And now this is an average over all fractions. It was known what the expected value of the size of this sum of partial quotients is. This is something that also Donald Knuth was very interested in, because this is a quantity that shows up in algorithms of some arithmetic nature, such as calculating the GCD of two numbers. So this was known, but as it turns out, in this problem here, the average value is different from the typical value. So the expectation is larger than the typical value. And this comes from the fact that the underlying distribution is what is called heavy-tailed by probabilists. So there is a relatively high proportion of fractions for which this quantity is very large. And this small proportion pushes up the average, the expected value, but the typical order of this sum of partial quotients is something smaller. Let me try to show this. So, okay, remember the average size of the sum of partial quotients by this result here is roughly log n squared. But now, as it turns out, the typical order is much smaller. It's log n double logarithm of n times some constant. So this is the main result of this paper that I'm advertising. So we consider all reduced fractions A over n. This denotes the sum of the partial quotients of A over n. The typical order is this 12 over pi square log n double log. And the whole thing here is, this is called the concentration inequality. It says the proportion of those fractions for which the actual value of the sum of partial quotients is far away from the typical value. So this is at least t log n far away for some parameter t. The proportion of these fractions is at most this and this much. So a lot could be said about the result here. It turns out the tail estimate here is optimal, but I don't want to speak about too much about the meaning of the result. I want to indicate how it's proved using some machinery from uniform distribution mode 1. Remarkably, one trivial corollary of the result is, so let's look back. So the typical behavior is this. Now it means, well, if I, so the proportion of fractions for which this actual value is away from the typical value by some quantity is at most something here. As soon as I get something on the right-hand side which is smaller than 1, it means that there exists a fraction which is at least as close to this typical value. So that a trivial corollary of the result is, for all n, there exists a reduced fraction for which the sum of partial quotient is at most typical order plus some error. We also have results on the size of the maximal partial quotient. I denote this by capital M, maximal partial quotient of A over n. For all n, there exists a reduced fraction such that the maximal partial quotient is at most, again, this is the typical behavior plus some errors. And the striking fact here is, so maybe many of you are aware of the results of Bourguin and Kontorovich on the Zaremba conjecture. For a set of full density of integers, Zaremba's conjecture is true. Now, to the best of my knowledge, if you want a result that holds for all n and not just for a set of denominators n which have full asymptotic density, the best result that's known is the one that's stated here. Similarly, the best result that's known for the sum of partial quotient, to the best of my knowledge, is this one here, which is a bit depressing. So it means the best existence results that we have that hold for all n, the best known existence results are the ones coming from typical behavior. And this is like a challenge for all young enthusiastic mathematicians who are listening here. Prove the existence of fractions for which these quantities are actually smaller than typical order. Okay, so let me try to briefly indicate how this is proved and where the uniform distribution comes in. So one fact, if you know a bit of continued fractions, this is our fraction a over n. If another fraction is very close to a over n, then it can only be a continued fraction convergent of a over n. Then if some fraction is a continued fraction convergent, then the difference between this continued fraction convergent and the fraction a over n contains the information on the size of the partial quotient. So this is the input from the Diophantine approximation. And now we have input of some sort of discrepancy type. So the point set of all these reduced fractions has somewhat small discrepancy. Okay, so this is a non-trivial statement. So here A runs only over coprime integers with n. If A contained all integers, not just coprime ones, then this would be trivial. The fact that the set of this coprime, these reduced fractions has small discrepancy, this is non-trivial. This comes from some CIF estimate. Okay, so this looks very complicated. Let me tell you what this means. Here we have this sum of partial quotients. Now here we take an extra summation over all possible denominators k and all possible numerators b of some other fraction b over k. On the right-hand side here, we have some weight function that has small support. Now this is designed in such a way that this contribution here on the right-hand side is only non-zero if b over k is a convergent, a continued fraction convergent of a over n. So that comes from the small size of the support of this function w on the right-hand side. Okay, so actually we only see a contribution here if b over k is a convergent of a over n. And now this function is designed in such a way that if b over k is a convergent, then the size of this function is the corresponding partial quotient. So we have rewritten a sum of partial quotients as a sum of function evaluations of some, well, weight functions evaluated at a over n. And now here comes the equidistribution. So this is just the right-hand side from the previous equation. Now I switch the summation over b and k. I move them to the outside. Inside I have the summation over all a which are coprime with n. And now here, this is some function evaluated at the points a over n. There is an average of over all points in this point set. As I said before, we do have a discrepancy type result for the distribution of all these fractions a over n. So now the uniform distribution machine kicks in. We can approximate this average of function evaluations by an integral. And now we continue calculating. Okay, so here, this is in a crucial moment, we use the information on the regularity of the distribution of the point set to approximate this average by an integral. Okay, we get a certain size of the integral, we sum up and so on, and we continue. So this is a, well, real world application of uniform distribution machinery in a contemporary research problem. If you want to read more about this, then I recommend to look at this recent arXiv preprint. Okay, so that's all the material that I presented for you. I hope this was interesting. Thank you very much for the attention.
Thank you.
Thank you. Thank you very much, Christoph. I enjoyed very much your talk and learned a lot. And now we have time for questions. Anyone can make a question.
May I ask?
If I'm not very good with this kind of question, but I'm very surprised that it does not depend on the nature of n.
Yes, you mean here in this result here in this concentration result? Yes, I don't know. So I didn't want to speak about too much about the particular meaning of this. As you may know, there is a result of Baladi-Vallée, which says that if you take an extra average over all denominators n, then there exists a limit distribution, and this limit distribution is explicitly calculated. And of course, it might happen that in this limit distribution, if you have this extra average over n, then you don't see any effect of the arithmetic nature of n, because it may just disappear after taking this extra average. And here, I'm not sure if one should have, well, you know, it is what it is, like it comes out this way. I'm not sure if one should have expected some arithmetic influence of n here. It might be, so as I said, we do know there is a limit distribution if we take this extra average over denominators n. Now in this setting here with fixed denominator, we don't know if there is a limit distribution. It might be the case that in the potential limiting behavior in this problem, maybe some other quantities depend on the arithmetic nature of n. So not the mean, maybe the variance, maybe some other moments, something could depend on the arithmetic nature of n.
Okay, thank you.
May I ask?
Sure, go ahead.
Okay, thanks. Can you say anything about the length of the expansion?
Yes, so this is also possible. So in actually the framework we have is a very general framework. So we have some function of the partial quotients. So for the length, you would just make the function being constant 1. We can also count how often one particular partial quotient shows up and so on. So that's relatively flexible, because really it just comes from this uniform distribution machine. You have this weight function W. You have to make sure that this W is somewhat regular, and then you can start running this uniform distribution machine. So yes, so we do get results of a more general nature. You have to look at the paper if you want to know it in detail.
I think it's interesting because it says a number of steps in the Euclidean algorithm if you compute the GCD of A and N.
Yes, exactly. So that's why Knus and such people were interested in this. I have to say, I find it very remarkable that this has not been calculated before. So for me, this would be this is a very natural quantity to calculate what this is, this typical order of this sum of partial quotient. I find it very strange that nobody calculated this before. There is this Russian school of Bikovsky and associated researchers who have been working on this a lot, but they only proved something like upper tail estimates and so on. They didn't figure out the actual typical order.
Thank you.
Okay, I have a last question outside this talk, because it's my own interest in the discrepancy model 1. And recently I was needing something about the rational numbers of the form log of prime divided by log of other prime. And so this is why I contact you by email and ask a lot of things. And do you know if there are do you know if can you say what is known about this typical this kind of rational numbers, or is just the approximation for these numbers?
Can you say again what the problem is, what the question is?
The question is, okay, so I see that there is a definition of measure of irrationality, correct? Is the exponent in the Diophantine approximation or something like this. And I only saw a result that that is from some years ago that okay, has a finite measure of irrationality. So it depends on the log of prime of the logarithm of the primes. And just want to know if perhaps you know something that can be better than this, like a constant for all the primes.
Okay, so you mean the sequence that you take is something like 1 times log of primes, 2 times, 3 times, and so on, something like this Kronecker sequence.
No, the rational number is log of prime divided by the log of other prime. And the sequence is n multiplied by this irrational number.
Okay.
Yeah. And I'm sorry about this because it's not directly connected with the talk, but and I was just curious if this is perhaps known in the literature or not. Something about these typical irrational numbers. Yeah. But okay,
I don't know. So I would expect logarithms of primes being complicated. Maybe it's difficult to handle this, but I don't know.
Okay, perhaps we can discuss this by email or
yes, sure.
Time.
Yes,
yeah. Okay, so I want to thank you everyone for coming, and thank you, Christoph, for the nice talk. So
thank you very much for the invitation.
Okay, so I'm glad that you like Brazil. I hope that at some point you can come back here.
Well, yes, you have to organize an actual conference. Yeah, maybe instead of an online seminar series, you should do a real conference once per week, like a full week in Brazil.
Yeah, that will be nice. Yeah. Okay.
Okay. Thank you for the invitation. Have a nice day.
Have a nice day.
Bye-bye.